Hello, this is Dr. Christy Patton Lukes, a chemical engineering professor at Missouri S&T. These video lessons are for our course in process control. The textbook that the lectures are based on is the fourth edition of Process Dynamics and Control by Dale Seaborg, Thomas Edgar, Duncan Mellichamp, and Francis Doyle III. This is a Wiley textbook. Now, for this portion of the material, the older editions are going to have pretty much the same information. They've leaned a little more heavily into some bio uh, kind of applications, and so you may wish to get the more recent edition. We are going to start looking at Chapter 2, Theoretical Models of Chemical Processes. In our mass and energy balance class, at the beginning of your chemical engineering education, we learned how to create these steady state designs and create these process flow diagrams. What we want to do now is extend that to look at dynamic models. Well, that begs the question, why do we need a dynamic model? We want to improve our understanding of the process in general. And this is going to help us develop new control strategies, especially for new processes. Or if we have an existing process, this allows us to optimize the operating conditions or to train plant operating personnel. We're going to be doing these balances on pencil and paper. We're going to use simulation software such as ChemCAD, Aspen, etc. The models that we're going to use, they may be theoretical. That's what we'll be working on right in today's lecture, but they also can be empirical. Okay, usually theory is best, but it can be really challenging sometimes. And so empirical equations can be great if you're really matching the conditions that they were designed for. Okay, so, you know, caution as we're doing this, but recognize that this is an important need. We have our general modeling principles. You should be familiar with our general rule that the amount that accumulates, so that's a change over time, is going to be the amount that comes in minus the amount that leaves, plus a rate of production, or minus a rate of consumption, if you prefer. And we applied this to mass, we applied this to specific components, and we applied this to energy, right? So we've done all of these various types of models. I wanted to remind you of one thing that as you're looking at models, a lot of times we'll use a delta notation to indicate a change or a difference in. Delta, if you are talking about systems with flow, means the out minus the in. And for systems with change in time, transient, then we talk about the final state minus the initial state. And so there is a sign, SIGN, associated with that delta. That will help you as we move forward. Now, I would like to remind you that when you were taking your mass and energy balance course, you developed a systematic approach to doing a material balance and energy balance, etc. Let's try to replicate that here, but we're adapting it to developing dynamic models, things where we've got changes in time. So, our first thing we need to do is decide what's the purpose of our model. So, state your objectives and your end use of your model so that you can determine how accurate the model needs to be. Don't put a lot of extra effort in that's not necessary, right? And sometimes seeing that written out will help remind you as you get kind of into the weeds of doing the model of whether or not something is truly worth it. And then next, I really strongly recommend draw a sketch of your process and label all the process variables. It is so helpful to have it on paper and to be able to look at a picture. Then list the assumptions that you're using. You want to aim for something simple, but you don't want to simplify it so much that the problem is trivial, right? You can just assume the whole problem doesn't matter, right? That's crazy, but you want to list the assumptions. And I find that I never get all the assumptions on my first pass. I come back and add to that list as I go. Then you're going to look at your process variables, and for each one of them, think about whether or not they will vary with the location in the system, or are they going to remain constant throughout? So, for instance, something, that's related to, say, density, volumetric flow rate, something like that, may not change much if your temperature isn't changing much, or maybe pressure and temperature. So think about those things. Can you consider something to be fairly constant or at least constant throughout one section? Okay, make those decisions. And then you're going to write the appropriate conservation equation. So the rate of change is what came in minus what comes out plus how much is generated. Okay. And then you're going to think about all those other equilibrium relations or other algebraic relations like the sum of x equals 1, those kinds of things, those other facts that you know, and write those down so that you can look at this and see whether or not you have enough information. Now, to do that, we do a degree of freedom analysis that determines whether or not our model can be solved. Basically, we're looking to see if I have as many unknowns as equations. And then simplify this as much as you can. It's really helpful if you can put it in the form of your output variables, the things you're wanting to be able to calculate is equal to a function of all the input variables. In other words, separate these two things out, okay? Even if it's a system of equations, the best you can do to separate that out, you will make things easier in later steps. And then you're going to look at all of those input variables. Maybe it's the flow rate in, maybe it's a changing pressure in, and try and decide whether or not you think this is something that is a disturbance that you have no control over, or maybe someone has control over it. Someone opened a valve and now you have a whole lot of extra flow. Okay. Um, but you didn't do that. So that would be a disturbance. Or maybe it's a change in the weather that caused a upheaval to the temperature. Okay. So those are disturbances. And then those that are manipulated, the things that you can change to affect a better dynamic system. Okay. And we'll be talking about these a lot more as we go through the course, but start thinking about it now. And if you begin with trying to classify all your variables, it will make later portions of the course easier. Let's talk about degrees of freedom analysis. You've done this in previous courses, you used this. This is basically where you find out if you have enough equations to solve for all of the variables you have. And it's just never quite as simple as it sounds like it's going to be, right? So having a process, a checklist can be very helpful here. So first, go through and figure out everything that you know to be constant. So likely candidates are things like density or C sub P, those properties, things associated with size. So diameter of a tank or cross-sectional area, maybe. You've got it simpler than that. Anything that you know to be a constant, make sure that you can identify that. Now, in the mess of a large problem, sometimes you get confused. You just forget that something is a constant. So I do find it very helpful if I'll like take a highlighter or something and mark all the things that I know to be constants. So I can kind of take them out of my thought process for these next steps. Then we're going to determine the number of equations. Okay, just count them. Don't forget about those things like the sum of x equations, things like that. And then n sub v is the number of process variables. So if it wasn't a constant, it's a variable. Count those. The difference between the number of variables and the number of equations is your degrees of freedom. Ideally, this would be 0, and then you can move on and solve your problem. Most of the time, yeah, not quite so much. So first, figure out which of the number of equations, okay, that's how many variables you can solve for. So look at the number of equations. If it was 3, then you can solve for 3 of your variables. Figure out which 3 those are going to be. Now, I'm going to recommend that it's probably the ones that you have listed in your derivatives, the d dt portion of a dynamic balance. Okay, so that took some care of some of them, but now you have the n sub f number, the extra variables you have. And so now you need to figure out how you can specify those. Are they a disturbance where I'm just going to have to come up with a model, like maybe the external temperature goes to a high value in the afternoon and a low value overnight, and I model it as a sine wave. Okay, that would be a fair thing to do. Okay, so I'm going to specify that disturbance. Or maybe it's just random noise. I can deal with that too. Not as easily mathematically, but I can deal with that. And then other variables are going to be manipulated variables, things that I might change. So I might change a flow rate by opening or closing a valve. I might, yeah, change a pressure, I could change anything. What is it that I'm going to change? Those are my manipulated variables. Okay, so let's identify those, have our plan for how we're going to solve things. All right, so far in this video, we have talked about things in a fairly, theoretical way. In our next lessons, we're going to be looking at examples. Now, I strongly recommend that you look at the examples in the book. Chapter 2 of this textbook has excellent examples, and I am not going to be working all of those. All right, see you in the next video.